Good day everyone, I'm Lord Anthony Arsula. Today, we are going to discuss about a priori algorithm. In this segment, we're delving into the fascinating world of the a priori algorithm. Developed in 1994 by Rakesh Agrawal and Ramakrishnan Srikant. The a priori algorithm has become a cornerstone in data mining and association role learning. Its significance lies in its ability to efficiently uncover meaningful patterns and correlation within vast datasets, making it a crucial tool for businesses and researchers alike. Throughout this presentation, we'll explore the inner workings of the a priori algorithm, its applicants, strengths, limitations, and how it compares to alternative algorithms. The a priori algorithm is a methodical approach to association role mining, particularly in transactional databases. Its bottom-up strategy involves gradually building item sets of increasing size until no more frequent item sets can be found. This process is guided by the a priori property, which states that if an item set is frequent, then all of its subsets must also be frequent. By following this property, the algorithm efficiently traverses the search space, identifying frequent item sets that meet the specified support threshold. Through a breadth-first search strategy, the a priori algorithm systematically explores the dataset, making it a reliable and widely adopted approach in data mining. Time complexity. Understanding the time complexity of the a priori algorithm is essential for evaluating its efficiency, scalability, and performance. The time complexity is typically expressed as where n represents the number of the transaction, m denotes the maximum number of items per transaction, and k signifies the maximum size of frequent item sets. This complexity arises from two major steps: candidate generation and trimming. These steps involve scanning the database multiple times to identify frequent item sets and prune infrequent ones. As the dataset size or the support threshold increases, the time complexity of the algorithm also increases, which can impact its scalability and practicality for large datasets. The candidate generation and trimming processes are the backbone of the a priori algorithm's time complexity. The candidate generation step involves creating candidate item sets of size k based on frequent item sets of size k-1, which requires scanning the database and checking the support of each candidate. Similarly, the trimming step involves pruning candidate item sets whose subsets are not frequent, requiring another scan of the database. As the number of transactions and the maximum number of items per transaction increase, the time complexity of these steps also increases, impacting the algorithm's overall efficiency. To address scalability concerns, optimizations such as using data structures and early stopping strategies can be employed.
Good day, I am Ivan J. Bagay, and I discuss our algorithm simulation. Now, let's take a closer look at the a priori algorithm in action through a visual simulation. By observing the algorithm's behavior, and decision-making process, we can gain a deeper understanding of how it works and its effectiveness in identifying frequent item sets. This simulation will walk us through the steps involved in discovering associations within a sample dataset, highlighting key concepts such as candidate generation and support counting. Please follow along as we explore the simulation and its implications of real-world applications.
Hello everyone, and welcome to this interesting session about Apriori algorithm. Now many of us have visited malls and supermarkets such as SA Moraria for household needs. Well, let's say that we are planning to buy a new laptop. What we would typically do is search for model by visiting the mobile section of the store, and then select the product and head towards the billing counter. But now, the goal of the organization is to increase their revenue. Can this be done by just pitching one product at a time to the customer? Now the answer to it is clearly no. Hence, the organization began mining data relating to frequently bought items. So market basket analysis is one of the key techniques used by large retailers to uncover associations between items. Now examples could be the customer who purchased laptop. 60% likelihood that they will also purchase mouse and bag. Customers who purchase laptops are more likely to purchase laptop bags as well. They try to find out associations between different items and products that can be sold together, which gives assisting in the right product placement. Typically, it figures out what products are being bought together, and organizations can place products in a similar manner. For example, people who buy a phone also tend to buy AirPods, right? And the marketing team at region stores should target customers who buy iPhone and AirPods, providing an offer to them so that they buy a third item, like cases. So if a customer buys the phone and buds and sees a discount offer on cases, he'll be encouraged to spend more and buy a case. And this is what market analysis is all about. This is what we're going to talk about in this session, which is association rule in mining and the imperial court. Association rule can be thought of as an infinite relationship. Just to elaborate on that, we have come up with a rule. Suppose if an item A is being bought by the customer, then the chances of item B being picked by the customer to under the same transaction ID is found out. You need to understand here that's not a causality. Rather, it's a co-occurrence pattern that comes to force. Now there are two elements to this rule. First is the if, and second is the then. Now if is also known as antecedent. This is an item or a group items that are typically found in an item set, and the later one is called the consequent. This comes along as an item with an antecedent group, or group of the antecedents approaches. Now if you look at the image here RB, it means that if a person buys an item A, then he also buy an item B, or he will most probably buy an item B. The simple example that I give you about the phone and the buds is just a small example. But what if of thousands and thousands of items with a data? If you go to any professional data scientist, you can just imagine how much of profit you can make if the data scientist provides you with the right examples and the right placement of the items, which you can do, and you can get a lot of insights. This is why associate rule mining is a very good algorithm which helps the business make profit.
next is the real-world simulation. In the real world of the a priori algorithm finds extensive applications, particularly in market basket analysis, aims to uncover associations between products purchased by customers, enabling businesses to understand consumer behavior and make informed decisions. For example, by analyzing transactional data from a grocery store, the a priori algorithm can identify common item sets, such as customers who frequently purchase bread and milk together. This insight allows businesses to optimize product placement, promotions, and inventory management strategies to enhance customer satisfaction and increase sales. And the next is all about the test cases. Evaluating the performance of the a priori algorithm requires rigorous testing under various scenarios and datasets. Test cases serve as standardized benchmarks for assessing the algorithm's efficiency, accuracy, and scalability. Popular machine learning libraries such as Python's scikit-learn provide a range of tools for conducting performance evaluations, including metrics like precision, recall, and F1 score. Additionally, visualization techniques can help analyze the algorithm's behavior and identify areas for improvement. By systematically testing the algorithm under different conditions, we can gain insights into its strengths, limitations, and optimal parameter settings. And the results and observations will be discussed by Mary Angeline Lehman.
Good day everyone, I am Mary Angeline Lemin and today we will proceed about the results and observations. Analyzing the results and observations from applying a priori algorithm reveals valuable insights into the dataset structure and associations. The algorithm effectively identifies frequent item sets and generates association rules with metrics such as support, confidence, and lift. These metrics quantify the strengths and significance of relationships between items, providing actionable insights for businesses and researchers. By interpreting these results, stakeholders now can make informed decisions about product recommendations, marketing strategies, and business operations, leading to improved efficiency and profitability. Next is performance evaluation. A priori algorithm is essential for understanding its strengths and limitations in practical applications. While the algorithm is conceptually simple and easy to implement, it may face scalability challenges with large datasets or high-dimensional data. Comparing its performance against alternative algorithms such as FP growth can provide insights into memory efficiency, runtime complexity, and scalability. Additionally, considering factors like computational resources, datasets, properties, and specific use cases can inform algorithm selection and parameter tuning for optimal results. Evaluation methods. When evaluating the a priori algorithm, comparing it with alternative algorithms like FP growth is crucial. FP growth often outperforms a priori in terms of memory efficiency and scalability, especially for large datasets. FP growth's ability to build a compact FP3 and generate implicit candidates gives it an edge in resource efficiency. However, the choice between a priori and FP growth depends on various factors including dataset size, computational resources, and specific requirements. For instance, a priori may still be a viable option for smaller datasets, prioritizing simplicity and interpretability.
In terms of memory efficiency, number of passes through the data, and scalability, FP growth typically surpasses a priori. FP growth's ability to generate implicit candidates and construct and FP3 contributes to its efficiency. However, the choice between a priori and FP growth depends on factors such as dataset properties and available computational resources. A priori simplicity and interpretability make it suitable for certain scenarios, particularly with smaller datasets. Algorithmic strengths. Despite its computational complexity, the a priori algorithm offers several strengths. Its simplicity and ease of implementation make it accessible to users across various platforms. Additionally, its scalability and efficiency, along with its capacity to handle large datasets and generate rules of any length and complexity, make it valuable tool for association rule mining. For example, in market basket analysis, the a priori algorithm can identify significant correlations between products, aiding businesses in decision-making processes aimed at increasing revenue and customer satisfaction. Limitation and challenges. Despite its strengths, the a priori algorithm has limitations, particularly concerning its computational complexity and scalability. The algorithm's needs for multiple passes through the database and the generation of numerous candidate item sets can lead to increased runtime and memory-intensive operations, especially with large datasets. Additionally, sparse datasets with minimal support for most item combinations may further exacerbate computational expenses. These challenges highlight the need for optimizations and alternative algorithms in certain scenarios. Comparative analysis. In a comparative analysis between a priori and FP growth, both algorithms have distinct advantages and disadvantages. FP growth often outperforms a priori in terms of scalability, memory efficiency, and the number of passes through the data, particularly with larger datasets. However, the choice between the two algorithms depends on various factors, including dataset properties, computational resources, and specific requirements. While FP growth may be more efficient in many scenarios, a priori remains a viable option, particularly for smaller datasets where simplicity and interpretability are prioritized.
This concludes our discussion on the a priori algorithm. I hope you understand and found this session informative. Thank you for your attention.